In today's lesson, we are going to go over the different types of chemical reactions that we see in biological systems. So first, let's talk about energy. So energy is the ability to do work, and we see this in chemical, electrical, mechanical, light, or thermal energy. Each form of energy can be converted to other forms of energy. For example, we have battery, where it uses electrical chemical gradient, being able to give energy to different things like light bulbs. Then we have two types of energy that are really important, and you probably remember these from like even elementary school or physics class. So there's kinetic energy, which is occurring as a result of movement. So for example, we have waves crashing against the shore, which can be used to harness other forms of energy. Falling rocks, moving molecules in a solution, and muscles contracting. Kinetic energy is useful because it can perform work by making other objects move. So we see here we have different examples. So we have an airplane flying, or a windmill rotating, a boy skateboarding, a woman cycling, car moving, or a boy playing soccer. All of these are different forms of kinetic energy. The other type is potential energy. So this is where we have stored energy that has the potential to do work. So in this example, we have divers. When they're up here, they have the potential to fall, and this would be potential energy when they're up here. As they're moving, this is kinetic energy. With the diver, the farther they are from the ground, the more potential energy they have. So looking at somebody with a bow and arrow, this was taken from last year when my student Dylan was in my class, grade 12 class, and he, as you're watching this, might be in the Olympics for archery. So I use this as the example, and now he will live on forever in the videos. So here, as the archer pulls back on the parts, pulls back on the bow with the arrow, this is potential energy. So at this point, nothing is moving. That arrow isn't moving, but it has the potential to move. Once the archer lets go of the arrow is in movement, and that is kinetic energy. So we're going to talk about the first law of thermodynamics. This states that the total amount of energy in the universe is constant, meaning that energy cannot be created or destroyed, but only converted. There's two types of reactions that we are going to talk about. One is endergonic reactions, and the other is exergonic reactions. So we're going to look at each one separately. So let's look at the axes so we understand what these graphs are telling us. So we have potential energy of molecules. So that's how much energy those molecules are storing. And then this is over time. And this is the same for each graph. Okay, so looking here, this is the beginning of the reaction, and this is going to be the end of the reaction. And we see the amount of energy from the beginning to the end of the reaction has increased in those molecules. So that means energy is going into those molecules. The endergonic reaction shows that energy has to be put into the reaction in order for it to happen, and there's going to be energy stored in those molecules. The example would be where we have glucose and fructose coming together to produce our waste product water and sucrose. So we see this when we have the building of molecules. Okay, so this is where we have energy put into molecules when bonds are forming. So we have a bond formed between glucose and fructose. And we'll look at some examples in a little bit. Okay, next we have an exergonic reaction. So in an exergonic reaction, we start with a high amount of energy. A little bit of energy has to go in to get the ball rolling for the reaction to occur, and then the reaction happens and a lot of energy is released. Okay, so when we start with a higher amount of energy and then energy is released, so the molecules have less energy. And we see this when we have the breaking of molecules. So in this case, we have oxygen and glucose, and we have a rearrangement happening where we have carbon dioxide and water. So we have a whole bunch of breaking of bonds happening, and energy is released. So that's an exergonic reaction. To better understand this concept, we're going to talk about bond energies for a little bit. So this is the measure of a covalent bond stability. So the more stable a bond is, the more energy it will have, the more energy that has to go into breaking it because it's so stable. So energy is going to be released or given off when a bond is formed. Okay, say that again. Energy is released when a bond is formed. So for example, when we bring glucose and fructose together, energy is being released. In the opposite direction, energy is absorbed, or energy is needed in order to break a bond. So let's look at some examples here. We have this chart, which is commonly found everywhere, especially in your textbook. We have the different bond types and the amount of bond energy that exists between those two atoms. Notice that as we increase the amount of bonds, you are increasing the bond energy. So a double bond has more energy than a single bond. In this example is between carbon and oxygen. And remember, the higher the bond energy value, the more stable the bond is. So again, let's look here at an example where, again, we have our potential energy within the molecules over time, so the progress of the reaction. So in this case, we have our reactants, carbon dioxide and nitrous oxide, or nitrogen dioxide. So these are the reactants, and we have this really interesting site or position of the reaction called the transition site. So this is where all of the bonds have been broken and they haven't been formed yet. So there's still this like rearrangement of molecules. So it's kind of the middle of the reaction. It's extremely unstable and it doesn't last long. So this is the amount of energy going into the reaction, at the starting of the reaction, and then we have this activation energy. So this is the amount of energy that has to go into the reaction in order for it to happen. So it's kind of like getting that a big boulder over a little bump in the road, and then it'll just roll on its own. So you have to put some energy to get things up here, and then it's just going to go on its own. So this is the activation energy. It's the energy between the beginning energy of the reactants and the energy of that transition state. And again, it doesn't last long at all. And then the difference between the beginning energy of the reactants and the energy of the products is your change in overall energy. So we see energy has been released here. So this is exergonic. This would be an exergonic reaction. So we're going to look at 4 different types of reactions. The first one is your most familiar one, which is the dehydration synthesis reaction, also known as a condensation. So it's the removal of water to bring 2 molecules together. So here is the formation of a peptide bond. So we have 2 amino acids, and we have the removal of a water molecule, which is the waste product. And we now have the peptide bond between the 2 amino acids. So what bonds are being broken? We have between carbon and oxygen has to be broken, so energy has to go in there, and a bond between nitrogen and hydrogen, so energy has to go in there to break the bonds. So looking, we have 359 kilojoules per mole to break the carbon and oxygen, again between here and here, and we have 391 kilojoules per mole to break the nitrogen and hydrogen. So in total, we have 750 kilojoules per mole that's to go into breaking those bonds. So that's the amount of energy in. Next, what is forming? We have a new bond formed between carbon and nitrogen, which isn't shown in this chart, but that's 305 kilojoules per mole being released. Okay, so even just comparing, we see more energy is going into breaking the bonds than is being released. So this is going to be an endergonic reaction. We have 445 kilojoules per mole that has to go into the reaction, and that's being stored in those bonds that is between the carbon and nitrogen now. So this is also called a not spontaneous reaction. That means a lot of energy has to go into the reaction in order for it to work. So it in no way would happen on its own. The other type of reaction we saw briefly when we were working with our molecular models, when you were asked to break apart it's actually a sucrose molecule by the addition of water. So in this case, we have a carbon and an oxygen bond breaking. You could think of it this way or this way, it doesn't really matter. But all you have is a carbon and an oxygen bond breaking. And that requires 359 kilojoules per mole. And then we have new bonds coming in. And we have a new bond between a carbon and an oxygen, and between an oxygen and a hydrogen. So we have carbon and oxygen is going to be releasing 359 kilojoules per mole, and the oxygen hydrogen will be releasing 459 kilojoules per mole. So lots more energy is being released as these bonds are forming. And we have a net of 818 kilojoules per mole being released, or an output. So this is called an exergonic reaction because more energy is being released from the reaction. It's also known as a spontaneous reaction. So energy still has to go in. If we saw, there was still that little hump for that activation energy, but it's only a little bit of a nudge that the reaction needs in order for our reaction to go. So they're considered spontaneous reactions. Next, for the chemistry people, this would be review, but for the non-chemistry people, this is probably brand new. So this is a oxidation reduction reaction. So this releases energy from the transfer of electrons from one reactant to another. And we see a lot of this in the upcoming units. So in this case, we have our X molecule is losing an electron and giving it to the Y molecule. So in this case, oxidation is the loss of electrons from one substance. So X has been oxidized. Similarly, the reduction would be happening to Y. So this is the addition of electrons to another substance. So one is always going to lose the electrons and another one is going to gain electrons, because remember, matter cannot be created or destroyed. It can only move from one thing to another. So X loses the electron, so X is being oxidized, and Y is being reduced because it's gaining the electron. And you can remember, the one way to remember this is we have our Y is gaining an electron, so its charge is going to become more negative. So it's being reduced. So that's how I always remember. Whichever one is getting the electron, its charge is becoming more negative, it's being reduced. Okay, a fun way to remember this is Leo the lion says grr. Lose electrons, loss of electrons is oxidation, gain of electrons is reduction. Often redox reactions are coupled, and we see this again coming up in this unit. So for example, molecule A is going to give an electron to B, so A is being oxidized, whereas B is being reduced. It's gained that electron. B then gives the electron to C, so B is then oxidized, and C is being reduced. And finally, C gives its electron to D, where D is now reduced, and C has been oxidized. The relative strength of oxidant agents, in this case, goes from A to B to C to D. So D is the strongest oxidizing agent. It has the strongest ability to pull the electron from C. So B pulls the electron from A, C pulls the electron from B, and D finally pulls the electron from C. So it's the strongest oxidizer. We see this in the electron transport chain, which we're going to learn about later in this unit, where we have different proteins complexes involved in transferring of electrons, where ultimately we end up with oxygen at the end taking the final electron, or being the final electron acceptor. And so every movement of the electron is A, releasing energy, and B, each subsequent protein complex is a stronger oxidizer. So the strongest oxidizer is oxygen at the end. So this would be the weakest over here and the strongest over here. And we'll see all the specific steps later on. Our last type of reaction is a neutralization, or an acid-base reaction. So this is a review from previous courses, but we get to look at it in a biological aspect. So this is where an acid and base combine to form a salt, and it's not always sodium chloride, but it's any kind of ionic compound, and water. So our poster child for an acid-base reaction or a neutralization reaction is where we have hydrochloric acid, which is an acid, sodium hydroxide, which is a base, react to produce sodium chloride, which happens to be salt, table salt, and water. And you can always remember salt water is produced. So buffers are really important in biological systems, and they minimize changes in hydrogen ion and hydroxide ions concentrations in a solution. So if you think different enzymes have a requirement for different pHs for them to function. So if we have everything neutralizing in our bodies and everything would have a pH of, like, say 7, then certain enzymes like pepsin, for example, wouldn't be able to function. So it's really important for our bodies to have buffers to maintain the proper pH in different parts of the body. So buffers maintain this, the proper pH, by donating or accepting hydrogen ions. And we're going to look at blood as an example. So here we have our red blood cells, and we have our epithelial cells, which are releasing carbon dioxide into the bloodstream. The blood cells are going to bring this carbon dioxide to the lungs for us to exhale as waste product. Okay, in this we have a specific reaction that occurs that could be very detrimental to our health depending on if it occurs too much or too little. So we're going to go to the next slide and we can look at it in a bigger form. So here we have water, which is a big part of our bodies, and we have carbon dioxide. Water and carbon dioxide can react to produce carbonic acid. Carbonic acid can then behave in a certain way. So if our hydrogen ion concentration becomes too low, it will release a hydrogen ion and become bicarbonate ion and hydrogen ions. And this allows our pH levels to become less acidic. Now, if it becomes too acidic, the bicarbonate ion can take up a hydrogen ion and go back and produce carbonic acid and become more acidic. And we have this transfer of the hydrogen ion from carbonic acid, or being released and producing the free hydrogen ion and bicarbonate ion in order to maintain the proper pH of our blood. And we see it's very important because we don't have a very large range of our pH for our blood for us to be happy. So our normal pH is between 7.35 and 7.45. You go higher than that and you end up getting alkalosis. Alkalosis, that's how it's said. And then eventually death if it gets too high. And then similarly, if it goes too low, you get acidosis. And then again, death once you get to, so sad, pH of 6. So the buffer system within our bodies is constantly undergoing this acid-base reaction in order to keep us healthy.